There is a place in the universe where everything ends, a place where light cannot escape, where time itself slows and bends and finally stops, a place that swallows stars whole, a place that has weight but no surface, a place that is darker than darkness because it has consumed all the light around it. We call it a black hole. For centuries, it was only a possibility, written in equations, suspected in mathematics, but never seen. Today, we know they are real. We have photographed them. We have measured their gravity. We have watched them devour entire suns. There are millions of them in our galaxy. There are hundreds of millions, perhaps trillions, in the universe. Some are small, only a few miles across, but heavier than the sun. Some are vast, billions of times the mass of stars, sitting in silence at the centers of galaxies, slowly consuming everything that drifts near. Tonight, we are going to step toward one of them, slowly, not to escape, but to understand. We will travel from the dying breath of a massive star to the moment a black hole is born. We will float gently toward the event horizon. We will pass through it into a place where no traveler has ever returned. And we will see, in slow detail, what it might be like inside. We will visit the supermassive black holes at the hearts of galaxies, including the one that lies at the center of our own. And we will learn the strangest truth of all, that black holes, these eternal, perfect prisons of darkness, are themselves slowly fading away, drop by drop, photon by photon, into the vast cold of cosmic time. There is no rush tonight. There is nothing to fear in this story. Just close your eyes or let them rest gently on the screen. Let your breathing slow. The cosmos is patient. It has waited 14 billion years to teach us about its dark places. It can wait for us a little longer. Welcome to Sleeping Galaxy. This is the story of what lies inside a black hole. Before we can understand a black hole, we must understand how one is born. And every black hole begins, in some way, with the death of a star. Not a small star like our sun. The sun, in its final billions of years, will swell, fade, and quietly cool into a faint white ember called a white dwarf. There is no drama in such an ending. There is no black hole. Black holes require something larger. A massive star, at least 20 times the mass of our sun, lives a brief and brilliant life. It is born from a cloud of cosmic dust drawn together by gravity. It ignites with hydrogen fusion in its core. For a few million years, it shines with extraordinary brightness, sometimes 100,000 times brighter than the sun. It burns with an intensity our small star will never know. But the cost of brilliance is short life. A massive star burns through its hydrogen quickly. When that fuel runs out, it begins to fuse heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon. Each new element fuses faster than the last. The star's core grows hotter, denser, more strange. It builds layer by layer like an onion of fire, and finally, deep inside the dying giant, the core begins to fuse iron. Iron is the end of the road. Every other element, when fused in a star's core, releases energy. That energy holds the star up against its own crushing weight. But iron is different. Fusing iron does not release energy, it absorbs it. In a single moment, in less than a second, the star's core stops fighting against gravity. It collapses. The outer layers of the star, suddenly without support, fall inward at nearly a quarter of the speed of light. They slam into the collapsing core and bounce outward in one of the most violent events in the universe. The star explodes. This is a supernova. For a brief moment, sometimes only a few weeks, the dying star outshines the entire galaxy that contains it. Its light travels for thousands or millions of years until, sometimes, it reaches Earth, and we see a new star briefly in the night sky. But that brilliant explosion is not the end. In the center of the supernova, where the core collapsed, gravity has not stopped. It has only just begun. The crushed remnant of the star, what remains of its iron core, is still falling inward. If the original star was massive enough, nothing can stop it. The core, which was already denser than anything in our experience, becomes denser still. Atoms collapse. The space between particles disappears. Then the particles themselves seem to vanish, pressed into a region so small the laws of physics begin to fail. In a single instant, all the mass of the star's core, sometimes 10 or 20 times the mass of our sun, is concentrated into a region smaller than a city, then smaller than a building, then smaller than a single point. A black hole is born. It happens in silence. The fire of the supernova fades over weeks and months. The expanding cloud of stellar debris drifts outward, carrying the star's heavier elements, the carbon, oxygen, iron, gold, and silver, into the surrounding galaxy. Those elements will, eventually, become new stars, new planets, perhaps even new life. But where the star's core once burned, there is now only darkness, a perfect, hungry, eternal darkness. It has no surface to land on. It has no light to shine. It has only gravity, gentle at first, far away, but growing more impossible the closer one approaches. It is no longer a star. It is a black hole. And somewhere, in fact, in many places, black holes are being born this way, even now, right now. As you breathe, as you rest, somewhere in our galaxy, the violent death of a massive star is folding itself into a perfect dark sphere. Quietly, distantly, with no audience but the cold stars. It is one of the most ordinary processes in the universe, and one of the most strange. Now imagine that we are traveling slowly toward a black hole. Not the supermassive kind, which we will visit later. a smaller one. A black hole formed from a single dead star, about 10 times the mass of our Sun, compressed into a sphere only 60 kilometers across, roughly the size of a small city. From very far away, this black hole would be invisible. It emits no light of its own. It has no glowing surface. If there is no matter falling into it, no gas, no dust, no doomed companion star, then it simply waits in the cold dark, drawing nothing toward it that is not already close. You could pass within millions of miles of a black hole and never know it was there. But as we approach, something begins to change. The stars behind the black hole start to look strange. Their light, traveling toward us from beyond, must pass close to the black hole's gravity, and gravity bends the path of light. The closer the light passes to the black hole, the more it bends. This is called gravitational lensing. Far away, we see the stars in their normal places. But near the black hole, those same stars appear smeared, stretched into thin arcs of light that curve around a perfectly black circle. Behind the black hole, stars that should be hidden become visible. Their light has bent around the dark sphere and reached our eyes from impossible angles. The black hole becomes a lens, magnifying and distorting the universe behind it. And in the very center, where light cannot escape at all, there is a perfect circular shadow, a region of pure darkness, ringed by streams of bent and twisted starlight. This is the visible boundary of the black hole. It is called the event horizon. The event horizon is not a surface. There is nothing solid there. If you sent a small spacecraft toward it, the craft would not crash. It would not even know, at the moment of crossing, that anything had happened. But the moment it passed the horizon, even by a single inch, it would be lost forever. Past the event horizon, the gravity of the black hole is so strong that escape becomes impossible. To climb back out, you would need to travel faster than the speed of light, and nothing in the universe can travel faster than the speed of light. So once a thing crosses the event horizon, it falls. It cannot stop. It cannot turn back. It cannot send a signal home. From the perspective of the universe outside, anything that crosses the horizon is gone, as completely as if it had never existed. The name event horizon comes from this fact. Beyond it, no event, no light, no sound, no message, no signal can ever reach us again. The horizon is the universe's most absolute boundary. For a stellar mass black hole, the kind we are approaching, the event horizon is small, only a few tens of kilometers across. The closer you approach it, the stronger the gravity becomes, much, much stronger than at the horizon itself. In fact, for a small black hole like this one, you would not survive long enough to reach the horizon at all. Long before you crossed the boundary, the gravity would tear you apart. Not all at once, slowly. Gravity grows weaker with distance, so the gravity pulling on your feet closer to the black hole would be stronger than the gravity pulling on your head. The difference over the height of a human body is normally tiny. We don't feel it on Earth. But near a small black hole, that difference becomes immense. Your body would begin to stretch. Your feet would be pulled downward faster than your head. Your bones would lengthen. Your muscles would tear. Eventually, your atoms themselves would be drawn out into a long, thin stream. The astronomer Stephen Hawking gave this strange process a name. He called it spaghettification. A long, thin, stretched body, like a noodle, falling slowly toward the dark. It is one of the most poetic and unsettling phrases in physics. There is no escape from spaghettification near a small black hole. It is gentle at first, perhaps imperceptible, then noticeable, then severe, then absolute. A traveler approaching the stellar mass black hole would not survive to see the horizon at all. But a different kind of black hole, much, much larger, is gentler. We will visit one of those soon. For now, just imagine the dark sphere ahead, the bent and twisted starlight curving around it, the empty silence, the slow, inevitable pull. Imagine standing at a safe distance and simply watching. The event horizon does not move. It does not pulse. It does not shimmer. It is perfectly still, perfectly black, perfectly silent. It has been there for billions of years. It will be there for trillions more. Now we will do something impossible. We will cross the event horizon. We cannot, of course, do this in reality. No information escapes a black hole. No traveler returns. We do not know with absolute certainty what happens past the horizon. But the equations of general relativity, the theory Einstein gave us 100 years ago, can tell us much. Let us imagine then. Let us walk slowly through what the mathematics describes. Let us begin by changing our destination. Instead of falling into a small, stellar mass black hole, where spaghettification would end us before we even reached the horizon, we will fall into a much larger one, a supermassive black hole. The kind that sits at the centers of galaxies, millions of times the mass of our sun. Inside such a black hole, the gravity at the event horizon is not extreme. The tidal forces, the difference in pull between your head and your feet, are gentle. You would not be torn apart at the boundary. You might not even notice the moment you crossed it. You could pass through and live for a while. So imagine yourself drifting feet first toward a vast black sphere at the heart of a distant galaxy. Behind you, the light of stars. Around, swirling glow of the accretion disk, the bright halo of gas and dust spiraling into the black hole, heated to extraordinary temperatures, glowing in colors of orange and white. Above you, the light of the entire universe, slowly being squeezed into a brilliant ring as gravity bends the photons around your body. You are falling. You feel nothing unusual. There is no wind, no pressure, no sense of motion. The black hole is patient. It pulls without urgency. The fall takes hours, then days. Then, gently, the universe begins to look strange. Behind you, the stars compress into a smaller and smaller patch of sky. The light from distant galaxies behind your back becomes blue-shifted, pulled toward the violet end of the spectrum, growing more intense. In front of you, the dark sphere of the black hole grows. It fills more and more of your vision. The accretion disk wraps around it like a ring of fire. You cross the event horizon. There is no flash, no sound, no warning. The mathematics tells us that, for a falling traveler, the horizon is invisible. You only know you have crossed it because you cannot return. Inside the horizon, the universe behaves strangely. What was once outward in space has become backward in time. To climb back to the event horizon would require you to travel into the past. And no one, not even falling into a black hole, can travel into the past. Forward in time leads only one direction now. It leads toward the singularity. The singularity, the heart of the black hole, is the point at which all the mass is concentrated. Mathematics tells us it is a region of zero size and infinite density, where space and time themselves come apart, where the equations of general relativity stop working. We do not know what truly happens at the singularity. The laws of physics, as we understand them, fail there. To know what is really at the center of a black hole, we would need a theory of quantum gravity, a theory that combines Einstein's relativity with quantum mechanics. Such a theory does not yet exist. For now, the singularity is one of the great mysteries of physics. But the journey toward it is described well by general relativity. Inside the horizon, time and space have switched roles. You cannot stop falling, just as on Earth, you cannot stop time from passing. You drift forward, toward the singularity, with no way to slow. The universe behind you becomes brighter, shrinks to a point. Eventually, that point disappears altogether. You are alone with the black hole. And then, slowly, the tidal forces begin to grow. For a supermassive black hole, the singularity is far inside. You may have hours, perhaps minutes, between the crossing of the horizon and the moment your body becomes a thin, stretched thread of atoms. The fall is gentle, then less gentle, then severe. Spaghettification, once impossible to avoid, finally arrives. Your body, your atoms, your every part, drawn into a single line, a single moment, a single point. You become, in the language of physics, part of the black hole's mass. Your information, perhaps, is preserved on the surface of the horizon, in some encoded form scientists are still working to understand. This idea is called the holographic principle, and it remains one of the most strange and beautiful ideas in modern physics. Or your information is lost, destroyed at the singularity, and that loss is one of the deepest puzzles in physics, called the information paradox. We do not know which. We know only that you would not return. You would become silence. You would become darkness. You would become, in the simplest language, part of the black hole. We have spoken of stellar mass black holes, small, born in the depths of single stars. But the largest black holes in the universe are different. They are vast, quiet, older than any single star. They sit at the centers of galaxies, almost every galaxy, and have been there, in most cases, since the universe was young. We call them supermassive black holes. The smallest among them are about 100,000 times the mass of our Sun. The largest are tens of billions of times more massive than the Sun. Their event horizons can be larger than our entire solar system. Light, traveling at 300,000 kilometers per second, would take hours to cross the event horizon of the largest known black holes. How they came to be, when they came to be, is one of the most active questions in modern astronomy. Some scientists believe they grew slowly over billions of years by absorbing gas, dust, stars, and smaller black holes. Others suggest that some supermassive black holes formed nearly intact in the very early universe, collapsed directly from vast clouds of primordial gas, never going through a star phase at all. Recent observations from the James Webb Space Telescope, launched in 2021, have found supermassive black holes already present when the universe was less than 1 billion years old. Their existence so early is difficult to explain. Astronomers are still working on the answer. In the year 2019, the Event Horizon Telescope, a global network of radio telescopes linked together to form a single virtual instrument the size of Earth, captured the first image ever taken of a black hole. It was the supermassive black hole at the heart of the galaxy Messier 87, 53 million light-years from Earth, 6.5 billion times the mass of our Sun. The image showed a glowing orange ring of hot, accreting gas surrounding a perfect, dark, silent void. For the first time in human history, we had seen the shadow of a black hole. In 2022, the same telescope captured an image of a much closer black hole. The supermassive black hole at the center of our own galaxy, the Milky Way. Its name is Sagittarius A star. Sagittarius A star is a smaller giant, only 4 million times the mass of the Sun. It sits 26,000 light-years from Earth in the constellation Sagittarius. From our perspective, it is hidden behind dense clouds of dust and gas, invisible to ordinary telescopes, but easily seen by the radio waves that the Event Horizon Telescope detects. It has been there for many billions of years. It will be there, in some form, for many billions more. As you read these words, the planet you are standing on, the Earth, is moving in its orbit around the Sun. The Sun, in turn, is moving in its orbit around the center of the Milky Way galaxy. That center is Sagittarius A star. We are circling a black hole. It takes our solar system about 220 million years to complete a single orbit around the supermassive black hole at the heart of the galaxy. We are about 25% of the way through the most recent orbit. The previous full orbit happened during the time of the dinosaurs. We are not falling in. The black hole is far enough away, and our orbit is stable. We will continue to circle it peacefully for as long as the Milky Way exists. But we are dancing, slowly, gracefully, without realizing it, with one of the most extreme objects in the universe. The supermassive black hole at the heart of our galaxy is mostly quiet. It is not actively feeding. It does not emit dangerous radiation. From your bedroom tonight, you cannot feel it pulling on you. Its gravity at our distance is no different from the gravity of any other large object in the galaxy. It is simply there, sleeping, patient, vast. A silent, dark heart around which 100 billion stars slowly circle. We have followed black holes from their birth in the violent deaths of massive stars, through their nature, into their hearts, and across the vast scale of supermassive galactic giants. We have, perhaps, given the impression that black holes are eternal, that once formed, they last forever. For most of the history of physics, that was thought to be true. Black holes were believed to be permanent. Once mass fell in, it stayed in. Once the black hole formed, it would exist for all time. But in 1974, a young physicist named Stephen Hawking discovered something extraordinary. Black holes, he showed, are not truly eternal. They are slowly fading away. Hawking combined Einstein's general relativity with quantum mechanics, the strange physics of the very small. And he found that, near the event horizon of a black hole, quantum effects allow the slow leakage of energy. Pairs of particles, constantly appearing and disappearing in the vacuum of space, can sometimes be separated by the gravity of the horizon. One falls in, the other escapes. The escaping particle carries away a tiny amount of the black hole's energy. And by Einstein's famous equation, that energy and mass are equivalent. The black hole loses a tiny amount of its mass. This faint, slow leak of particles from a black hole is now called Hawking radiation. It is incredibly weak. A black hole the mass of our Sun would emit Hawking radiation at a temperature so cold, 100 millionths of a degree above absolute zero, that it is, in practice, impossible to detect. Such a black hole would take longer to evaporate than the current age of the universe, raised to a power of itself. The numbers are so vast that they have no physical meaning. They are mathematical only. For all practical purposes, large black holes do not evaporate. But small black holes, if they exist, evaporate faster. The smaller the black hole, the brighter and hotter its Hawking radiation. The faster it loses mass. And as it loses mass, it becomes smaller still, and its evaporation accelerates. Some scientists believe that very small black holes, called primordial black holes, formed in the first moments after the Big Bang, when the early universe was dense enough for tiny black holes to spontaneously appear. Most of these primordial black holes, if they formed, have already evaporated entirely. Some, the slightly larger ones, would be evaporating today at this exact moment in distant corners of the universe. When a primordial black hole reaches its final moments, the evaporation becomes a burst, a flash of high-energy radiation, a final, brief, brilliant goodbye. We have not yet observed such a flash. Astronomers are searching. For the supermassive black holes, the giants at the hearts of galaxies, evaporation is a process beyond imagining. They will outlast the stars. They will outlast the galaxies themselves. In the deep future of the universe, when all the stars have burned out, when matter has spread itself thin across an expanding cosmos, when even the protons in atoms have decayed away, the black holes will still be there. Slowly fading, bit by bit, photon by photon. The very last things to exist in the universe will be the largest black holes, slowly emitting Hawking radiation, slowly losing mass over timescales of 1,000 times the current age of the universe. And then, in the very final moment, even they will fade. The universe will be left in absolute silence, absolute darkness, absolute emptiness. Nothing will remain. This is the deepest, slowest, quietest end, the end that physics predicts for our cosmos. It is unimaginably far away. It will not affect you tonight. But it is good, sometimes, to think about how vast the universe is and how patient. To think about how small we are in the grand scale of cosmic time. To think about how quiet, how peaceful, how endless the dark places of the cosmos truly are. The black holes, these strange, terrifying, beautiful objects, will in the end go gently. They will not roar. They will not collapse. They will simply fade, like everything eventually must. We have come to the end of our journey. We have walked among black holes. We saw a massive star reach the end of its life, its core collapsing, its layers exploding outward, its center folding into a perfect dark sphere. We approached the event horizon, that absolute boundary between the universe and the dark, and learned how its gravity bends the very paths of light. We crossed the horizon. We drifted slowly into a place where space and time have changed roles. We followed the long fall toward the singularity and recognized that some questions are not yet answerable, even for our deepest theories of physics. We met the supermassive giants, the quiet hearts of galaxies. We learned that we ourselves orbit one of them, peacefully, every 220 million years. And we stood at the edge of cosmic time and watched the patient evaporation of black holes. Slow, faint, eternal. Black holes are not what they seem. In stories, they are violent, hungry, terrifying. In physics, they are the slowest, the most patient, the quietest objects in the universe. They wait. They draw in only what falls toward them. They emit no light, but they do, slowly, leak heat and time into the surrounding cosmos. They will outlast the stars, the galaxies, even most matter itself. They are the final guardians of cosmic darkness. You orbit one tonight, 26,000 light-years away, at the heart of our galaxy. Sagittarius A star is patient and silent. It does not move quickly. It does not threaten. It is simply there, holding the Milky Way together with its enormous gravity, around which 100 billion stars slowly drift. And around one of those stars, our sun, drifts a small blue planet. And on that planet, a small, warm being, breathing softly, listens to a story about the dark places of the cosmos. That is you. You are here. You are alive in this rare and precious moment, on this rare and precious world. The black holes will continue after we are gone. They will continue after the Earth is gone. They will continue after the stars are gone. But none of that, tonight, has to disturb you. Tonight, the universe is here. The galaxy is here. The black hole at its heart is patient and silent and far away, and you are warm, breathing, resting. Sleep well. The cosmos keeps watch. Good night.